Welcome back. Now that we introduced the concept of least squares, let's try to translate this concept into a mathematical form and find an analytical solution for it. Coming back to our line fitting problem, we are trying to determine what a good solution would be for this inconsistent system of equations. Say we have a solution x hat. The least squares principle states that the best solution for the unknown parameters in the vector x is the one which results in the set of new adjusted observations y hat, which is the closest or has a minimum distance to the original observation vector y. In a mathematical form, this condition of closeness or minimum distance for a particular estimate x hat is defined as the length of the vector e hat. This vector is the remaining part of the vector y with respect to y hat. And so, in the rest of this course, we call it the vector of residuals. So, based on the least squares principle, the least square estimate should minimize the length of the error vector, or the difference between observation vector y and ax. The length of the error vector, or the norm of the vector e, is defined as the square root of the summation over s squared elements of the vector. Note that the summation under s square root can be written in the vector form as E transpose E. The least square estimate of the unknowns parameters can then be found by the minimization of the norm or length of the vector E. The minimization of the norm of the vector is equivalent with the minimization of its s square norm. So, we can compute the least square solution by minimizing the s squared norm of the vector E. Recall that the vector of residuals or error vector is the difference between the observation vector y and the adjusted observation vector, which can be computed by ax. By inserting y minus ax instead of e, the minimization problem can be written as minimizing the s squared norm of y minus ax. Therefore, as we can see, x hat of least squares minimizes the sum of the s squares of the error vector e. This is actually the main idea behind the name least squares. We know from calculus that in order to find a solution to this minimization problem, we should take the first derivative from this multivariate objective function and set it to 0. From calculus, this first derivative can be derived as the following. By the way, if you are interested in the detailed mathematical derivation of this derivative, please look at the reading materials of this week. Now, by setting this derivative to 0, we get a transpose ax equals a transpose y. This new equation is called normal equation. The solution to the normal equation provides us the least squares estimate. The solution can simply be computed by taking the inverse of the left-hand side of the normal equation and multiply it by its right-hand side. The least squares estimate is then computed as inverse of A transpose A multiplied by A transpose Y. Therefore, if we have an observation vector Y and a design matrix A, we can simply put them in this simple equation and compute the least squares estimate of x. To summarize, for any given estimation problem, when we relate our unknown parameters x to observations y, using a functional model described by the design matrix A, the least square estimate can be computed by this simple equation. In addition to x hat, the least squares estimate of observations y hat can be also computed by inserting x hat into the functional model. And finally, the least squares estimate of residuals e hat can be also computed easily as a difference between the original observations in vector y and the adjusted observations in y hat. Now that we know all about the mathematics of least squares, let's look at its application to our line fitting problem and also at some more exercises.